Hello, in this video I want to explain about the logarithmic and exponential equations. We already know the properties of the logarithms and we know the definition of a logarithmic function. So we know that y is equal to the logarithm in base a of x if and only if x is equal to a to the y. So using this relation that exists between the logarithmic functions and the exponential functions that we know are inverse of each other, then we can solve some logarithmic equations. In the first case, I have the logarithmic equation log of x plus 6 equals 1. As I explained before, when we have just log, it's because it's the logarithm base 10. So we can rewrite this as log in base 10 of x plus 6 equals 1. Now, once you have uh, your logarithmic equation showing the base of the logarithm, you can now rewrite this logarithmic equation into exponential form. So you can say that 10 to the 1 is equals to x plus 6. So 10 to the 1 is 10, so 10 equals x plus 6. You solve for x, so you get 10 minus 6 equals x, so x equals 4. So you have now that x is equal to 4. It's important now to make sure that the argument of the logarithm is still greater than 0. So if you substitute this x here by 4, of course you will get a number as argument of the logarithm which is greater than 0. Another way to check, of course, if your solution is correct, you know that this is a logarithm base 10. So you say log in base 10 of x plus 6, but you know that x is 4, so you say 4 plus 6 equals 1. So you get log in base 10 of 10 equals 1. And we know that the answer is correct because remember that we have one property. Let's say that the log in base a of a is equal to 1. So yes, the answer or the solution of this logarithmic equation is 4. We have another logarithmic equation here. There is log in base 3 of 3x minus 1 equals 2. In this case, the base of the logarithm is explicitly there. So we will rewrite this in exponential form. We will say that 3 to the second power is equals 3x minus 1. So 9 is equals 3x minus 1. So adding 1 to both sides, you get 9 plus 1 equals 3x, right? And then, of course, you get that 10 is equals 3x, so x is equals 10 over 3. Again, you must make sure that when you substitute the x by the value you found here, that is a solution of the equation, the argument of the logarithm is still greater than 0. So when you substitute this x by 10 over 3, this would be, of course, 10 minus 1, 9. 9 is greater than 0, so that would be correct. That would be okay. Now, we can also double check this, uh, you know, to see if the solution is correct. In this case, substituting the x by 10 over 3. So we say log in base 3 of 3 times 10 over 3 minus 1. This is 2. 3 times 10 is 30 over 3 is 10 minus 1 is 9. So we get the log in base 3 of 9 is equals 2. You can now rewrite this as log in base 3, what is 9? 3 squared is equals 2, and we know that the log in base 3 of 3 squared is equal to 2, so 2 equals 2, which is true. Then we know that the solution 10 over 3 is correct. The property that I have used to know that log in base 3 of 3 squared is equal to is the property that said log in base a of a to the r is equals to r. So yes, in this case, the solution of the equation is 10 over 3. In these two examples, I have solved the equation by using, the relation between logarithmic statements and exponential statements. In my next example, I have two logarithmic equations. Now to solve these logarithmic equations, we're going to use a different property. So we know, based on the property of logarithms that we already studied, that if the log in base a of m is equals to the log in base a of n, then m is equal to n, where m, n, and a are positive, and a is not equal to 1. So if I have to solve an equation like the first equation, the first I have to use is to use the product rule. So you know that if the log in base a of m plus the log in base a of n, this would be equal to the log in base a of m times n. So we get the product of the arguments of the two logarithmic expressions, right? So I will just apply this property here. So we say that this is log of x times x plus 15, and this is equals to, I will just multiply this x times x plus 15 using this distributive property. I will also make visible the base of this logarithm, that is the common logarithm, so it's base 10. So we rewrite this now as log in base 10 of x squared plus 15x equals to, right? Now we're going to convert this into an exponential statement. So we say 10 squared is equals x squared plus 15x, right? Now we're going to, of course, say that 10 squared is 100 equals to x squared plus 15x, right? And now we're going to rewrite this equation in a standard quadratic form. So we get that 0 is equals x squared plus 15x minus 100. Now we're going to factor, so we get 0 equals, factoring, we're going to get x plus 20 times x minus 5. Just double check your factorization. 20 times negative 5 is negative 100. 20 minus 5 is this positive 15 you see over here. Then now solving these equations, this quadratic equation, we get that x plus 20 is equal to 0. So, sorry, x plus 20 equals 0. So x is equals negative 20. And the other solution is x x minus 5 equals 0. So x equals positive 5. Now again we have to go and substitute the x by x values. So when you substitute x by minus 20, when you say that x is equals negative 20, then the equation becomes log of negative 20 plus the log of negative 20 plus 15 is going to be negative 5 equals 2. We know that the logarithm of negative 20 is not defined. The logarithm of negative 5 is not defined, right? We can calculate logarithms only for numbers that are greater than 0. So that means that we have to reject this solution. Now, when you check your solution, x equals 5, this would be then log of 5 plus the log of 5 plus 15 is 20 equals 2. That should be good because the log of 5 exists and the log of 20 exists. So this solution can be accepted. So we're going to get, in this case, we have only one solution, and that solution is just 5. So the solution of this equation will be 5. So negative 20 is not a solution of this logarithmic equation. We have a second logarithmic equation here that is going to be solved using pretty much the same approach, except that in this case we're going to use the quotient rule. Let's say that the log in base a of n minus the log in base a of n is equal to the log in base a of m over n. So using this quotient rule of the logarithms, I can say that, log of 2x minus log of x minus 3 equals 1 is the same that, well, log of 2x minus the log of x minus 3 equals 1. I will just rewrite this as a quotient. So we say log of 2x over x minus 3 equals 1. We know that this is logarithm base 10, right? Because it's common logarithm. Then now we're going to rewrite this as an exponential statement. We're going to say that 10 to the 1 is equals to 2x over x minus 3. So now we can, let me just do this line to separate the two exercises. Now I can say that 10 is equals to 2x over x minus 3, right? So we can say now that 10 times x minus 3 is equals to x, right? So we apply distributive property, we get 10x, 10 times negative 3, negative 30 equals to x. We're going to solve for x, so we get 10x minus 2x equal 30. 10x minus 2x is 8x equal 30. X is equals 30 over 8. So x is equals 15 over 4. So 15 over 4 is a number greater than 3. Okay, so 15 over 40 is 3 over 4, so it's 3.75. So when you substitute the x here by 15 over 4, this number will be positive and this number will be positive, right? So 15 over 4 is not going to undefine the logarithmic expression. So if we did everything correct, right, if we didn't miss any any step, or sorry, we didn't make any mistake in the calculations, then this answer should be correct. So the answer here should be then 15/4. So here we got the solution of this logarithmic uh, equation. Now let's see now some exponential equations. So when we studied exponential equations, we were working with exponential equation with the same basis. When we have exponential equation with the same basis, we can use this theorem that say that if a to the u is equal to a to the v, then u is equal to v, right? So what we have to do, we have to try to get the same basis in both sides, right? So we have this 4 to the power of 2x plus 1 equals to 16. We know that is equal to 4 squared. Then now we have the same basis. We can say that 2x plus 1 is equals to, so 2x is equals to minus 1. So 2x is equals 1. Solving for x, now we have that x is equals then 1/2. So the solution of this exponential equation is going to be now 1/2. In this case, we have an exponential equation where, by making a very simple transformation that it is rewriting 16 as 4 squared, we can get the same basis and we can apply the theorem. Now, we have some exponential equations where doesn't matter, what you try to do, you have different bases and there is no way to get the same base. In this case, we're going to apply logarithms, to solve these exponential equations. We recommend to use the natural logarithm. So I will apply natural logarithm to both sides. I will say natural logarithm of 2 to the power of x plus 1 is equals to the natural logarithm of 5 to the power of 1 minus 2x. So now, using property of logarithms, I can write this power as a factor. So I can say that x plus 1 times the natural logarithm of 2 is equals 1 minus 2x times the natural logarithm of 5. We now apply distributive property, so we say x times the natural logarithm of 2 plus 1 times the natural logarithm of 2, which is natural logarithm of 2, is equal to 1 times natural logarithm of 5, which is natural logarithm of 5, minus 2x natural logarithm of 5. Now we're going to group the expression with variable x in one side of the equation and the expression without the variable x in the other side of the equation. So we can say that x times ln of 2 plus then 2x ln of 5 is equals to ln of 5 minus ln of 2. We have a common factor x here, so we're going to factor the x out. So we get x times ln of 2 plus 2 ln of 5 equals ln of 5 minus ln of 2. And then now we divide and we get that x is equals ln of 5 minus ln of 2 over then ln of 2 plus 2 ln of 5. And this is what is called the exact solution of the logarithmic equation. If now you want to find the approximate solution, then you will have to evaluate all these logarithmic expressions. So the solution, I will just write the solution, as an exact solution like that. So we say this is ln of 5 minus ln of 2 over then ln of 2 plus 2 times ln of 5. You can just do the work and evaluate that solution later if you want to find the approximate solution. Then now let's see the other case. We use a different color. So now we have the equation, the exponential equation, pi to the power of 1 minus x equals e to the x. So I will again apply natural logarithm to both sides. I will say ln of pi to the power of 1 minus x is equals ln of e to the x. Now we can write exponents as factors, so you can say 1 minus x times ln of pi equals x times ln of e. We know that the natural logarithm of e will be 1, so we get then now that 1 minus x ln of pi is equals to x. We apply distributive property here, so we can say that 1 times ln of pi is ln of pi minus x times ln of pi is x ln of pi equals to x. Then we're going to be adding x ln of pi to both sides, so we get ln of pi equals x plus x ln of pi. We're going to take a common factor x out, so we can say that ln of pi is equals x times 1 plus ln of pi, and then we're going to divide both sides by 1 plus ln of pi, so we get that ln of pi divided by 1 plus ln of pi is equals to x. And again, we found the exact solution of the logarithmic equation, so I can say that the solution here is ln of pi over 1 plus ln of pi. You can also, in this case, evaluate later, those expressions to find the approximate solution. Remember, these are the exact solutions, so you can evaluate to find the approximate solutions of these equations. My last example is this example where we have an exponential equation that is quadratic in form. So let's see how we can solve this exponential equation quadratic in form. When you see this exponential expression here, 2 to the power of 2x, you know that you can rewrite this as 2 to the power of x squared plus 2 to the power of x minus 12 equals 0. You can now make an appropriate substitution. In this case, an appropriate substitution would be to substitute 2 to the power of x by u. So then now you get that u squared plus u minus 12 is equal to 0. It's very easy to solve this equation now by factoring. So you can say that this is u plus 4 times u minus 3 equals 0. 4 times negative 3 is negative 12. 4 minus 3 is positive 1. So you get that u plus 4 is equals 0. So u is equals minus 4. And u minus 3 is equals 0. So u is equal positive 3. Well, now we have to again substitute, but in this case substitute u by the expression 2 to the x. So you will get that 2 to the x is equals minus 4. So you don't get any solution from this equation now. Why? Because 2 to the x will be greater than 0 for x, so it doesn't give you any solution. Then The other one, you have u equals 3, so you substitute the u by 2 to the x. So you get 2 to the x equals 3. You apply natural logarithm to both sides. So you say ln of 2 to the x is equals to the ln of 3. Now you rewrite this exponent as a factor. So you say x ln of 2 is equals to ln of 3. You divide by ln of 2. So you say x equals ln of 3 over ln of 2. Sorry, ln of 2. And then this is the exact solution of this equation. Is you calculate with your calculator, the approximate solution would be approximately 1.585. So you have that your solution is ln of 3 over ln of 2, or as an approximate solution, you could say that the solution is 1.585. So in this video, I just gave you some examples of the solution of exponential and logarithmic equations. In a future video, then we're going to discuss the in this case applications of the logarithmic and exponential equations. Thank you for your attention.